so welcome to this seminar today. It will be given by Shi Jin from Shanghai Jiaotong University. It is a common work with Nana Liu, who is here. And Shi Jin will be here one more week in the laboratory, so you can meet him in the other corridor. And today the talk is about quantum computation for partial differential equations.
Thank you very much. Thank Benoit for arranging this visit and also arrange this talk. So I've been stuck in China for 3 years. So it's really, I'm very happy to finally to get out and come back to Paris. Actually, Paris was my last visit before the pandemic. So today I'd like to talk about a project I've been involved with my young colleague, Nana Liu. She's really the expert on quantum computing. I'm a beginner, actually. So I learned all the quantum computing from her. So it's a project we started about a year ago. Try to use quantum computer to solve partial differential equations. So this is the outline. Well, so first I would give a very brief introduction for what people do in quantum computing, what it means. If you are expert, I apologize. So it's really what I call survival kit. It's basic knowledge you need before you do quantum computation. Then, if time allows, I will talk about 3 things. One is what we call a shorting virtualization of PDEs to make PDEs that can be solved by quantum computer. Then those are linear PDEs and ODEs. Then I will talk about some nonlinear PDEs and ODEs. If time allows, I'll talk a little bit about the topic which is related to uncertainty quantification. All right, so why we need quantum computer in the first place? Well, we all know classical computation is almost reaching its limit, right? I mean, there's this Moore's law which says every 18 months, the speed of computer will double. But now the computer chips now is in the few nanometers. So we almost reached the limit of Moore's law. So if you really break through, quantum computer might be the next hope. Of course, there are other issues with classical computations. You have a restriction on bandwidth, costs a lot of energy. For example, if you want to do an AI simulation like ChatGPT, if you want to train big data set for the train ChatGPT, I mean, it costs a lot of energy, okay, and the memory and time. So these are all these restrictions. So the concept of quantum computing actually came about 40 years ago by this gentleman. Everybody recognizes Richard Feynman. So he was asking the following question. He said, can a computer just be made to efficiently simulate quantum mechanics? We know, I mean, the probably most challenging problem to physically is to solve about the Schrödinger equation, I mean, which is usually dimension of several hundred. Okay. So the classical computer certainly is not enough to do that. So can one make a machine, quantum computer that can solve quantum mechanics? So the machine should be designed using quantum mechanics principle. Okay, so that's the idea. And he even imagined how the computer should be built using the so-called arrays of spin one-half particles, which actually corresponding to now what we call the quantum bits or qubits. So why we need to build a quantum computer? Well, it's generally believed, okay, you may not have to agree, quantum computer is probably the biggest engineering project of this century. Maybe along with AI, those are the driving force for the next generation of technology innovation. And if you really have it, it's going to change the world, okay, believe it or not. And up to now, people sort of, there are examples where the quantum computer can provide up to exponential speed up in a number of areas. For example, in factoring, cryptographic applications, in simulating physical systems, topological data analysis. And it could also provide up to a polynomial speed up in like searching algorithm, optimization, machine learning, and so on. So all the government begin to put a lot of money. All right, so this is data of 2020. So this is China, biggest investor, $10 billion for probably next 10 years. Where's France? Oh, here's France. Still also a lot of money. If you like money, so that's the area to go for. This is a European quantum flagship. And the US. Well, these are the figures, right? But there are, I mean, a lot of private companies. Even yesterday, there's a big Nature paper published by Google on quantum computers. All these giants of industry, Google, IBM, they're putting lots of money into this research on top of the government investment. All right, so next I will just give you some very elementary things, mathematical descriptions about what quantum computing is. We're all familiar with the classical computation, basically represent all signals by this 0 and 1, a string of 0, 1, these codes. And you start with electric signals of this type, you pass through classical gates, then you output signals of the same type. But quantum computer, actually, you have to start with so-called quantum state, all right? Then you pass through some quantum gates, which are unitary operators or unitary matrices. And then, of course, you will generate quantum states. All right. So quantum computer just start from quantum state, and you generate the quantum state. Of course, quantum state is usually not the information we want. What we want, for example, if you solve Navier-Stokes equation, you want to know the velocity, temperature, stress, and those things. Then you have to take so-called measurement. You have to extract information, classical information from quantum state, but that usually costs a lot. Okay. So basically, the quantum is kind of subroutine from you start with quantum state and quantum state. Then, if you have classical data, you have to do encoding. You have to transfer classical data into quantum state, and output you have to extract information, classical information, from the quantum state, which usually costs a lot. It costs so much that you may destroy quantum advantage. So this is so-called encoding and decoding. Actually, is a bottleneck for successful application of quantum computation. So when you do quantum computing, you start with these bits. These are basically 2 unit bases in L2 space, okay, 0 and 1. This is a linear combination of these 2 bits. Here are the coefficient A and B complex numbers, all right, and normalized to 1. So it's just a unit. So that's 1 qubit. So here we use Dirac notation for cut, precise cut. So that's just 1 qubit. If you have like m qubits, you just do tensor product, all right? So here we're going to work on basically a complex Hilbert space in capital N dimension. And usually we represent capital M by 2 to the power n, but this little n is so-called qubit, all right? So therefore, if you have a quantum algorithm, usually it's a polynomial of little n, while the classical algorithm is a polynomial of capital N. So the relation is exponential, there's exponential difference, which is the reason the quantum advantage can be up to exponential, okay, if you use these qubits. So the quantum gates are performed through very basic matrices. Okay, so here we just list a bunch of 2x2 unitary matrices. For example, Pauli matrices. These are just 3 standard Pauli matrices. This is called a gate, phase gate. So these are just the 2x2 unitary matrices. This is a very popularly used gate called control knot. So it's a 4x4 matrix. The first 2x2 submatrix is just identity. And then here you have you switch the last 2 rows of identity matrix. For example, if you have two qubits, so these are the basis vectors, all right? It's like in a 4-dimensional Euclidean space, you have these basic vectors. If you operate this control knot gate toward this basis function, then clearly the first 2 vectors remain unchanged. And the last 2, where you will just simply switch. Okay. It's not full screen, so I missed the last row, sorry. It turns out those matrices in the previous slides are all you need to do quantum computation. So there's something called a universal quantum gates. Those are the ones you have seen in the last slides are enough to carry out quantum computation. So this is something called a universal quantum gates theorem, which says, given any unitary matrix, it can be approximated by one or many of those in the previous slides up to any precision. Okay. So therefore, that's all you need. But of course, if you want to work only on the real space, then you may need this Toffoli gate, which is called a control gate. Also, it's for 8x8 matrix. The first 6x6 is identity, and the last 2 is this control. All right. So these are basically all the gates you need to carry out the quantum computation. So quantum computing is basically, I was telling still, you probably don't need to learn quantum mechanics. All you need to know is linear algebra, basically. So usually you draw a quantum algorithm by this kind of quantum circuits. So here, if you start with quantum state per psi, you multiply by unitary matrix, you end up at U per psi. All right. So for example, if this is the first Pauli matrix, you act on 0, you get 1, and so on. Well, this control knot gate. So it's if you work on 2 qubits, A is 0, it remains 0. If A is 1, you add to B. Of course, here the summation is mod 2, so it's 2 equals 0. So this is a very important algorithm to get, for example, eigenvalues. Yeah, in the last QPD, you act on some matrices continually. It's very much like power method. When you find eigenvalues of matrix, use power method. You keep multiplying by the same matrix. All right. Okay. So if you do that, that guarantees that you start with quantum state, multiply by unity matrix, you end up with the quantum states. And if you want to get classical data, you have to do so-called measurement. All right. So in a sense, these quantum algorithms are kind of subroutine. And at the beginning, at the end, you have to convert that into classical data or vice versa. So that's called a quantum measurement. And in the measurement, you have to measure the probability of certain outcome, okay, in the computational basis. And this part usually cost a lot. For example, you can do Monte Carlo. I mean, that's classical algorithm. So if you do that, of course, the quantum advantage you gained will be completely lost. So this measurement is bottleneck if you really want to use quantum computation. So there are, of course, a lot of challenges, both hardware and software challenges. The major problem is that now, if you do not have many qubits, there are a lot of noise, environmental noise, which is, so you can compute, if you compute a long time, it's result are not reliable. Or yesterday, actually, this breakthrough by Google, where they have enough control gate, logic gates which allow them to reduce the noise. All right, so this noise create errors. You have to do error corrections, which is usually very difficult. All right, and so there are a lot of hardware challenges. We don't know when we're going to have a computer that can be used, but we hope that before too long. At the software level, there's also challenges because you really need new softwares, and it cannot debug. In classical computation, usually if you want to see whether you this bug, you just stop your calculation, you print out the result and you see, right? But a quantum computer, you start from the beginning, you have to compute all the way to the end. You cannot stop to check, because once you stop to check, you have to do this measurement. And then, of course, you lose your quantum advantage. So you cannot debugging, basically, all right? And also the algorithm design is very difficult because I always say quantum computers like not even baby, it's like an infant. You have to supply infant with formulas that the infant can digest. So you have to write the algorithm in a way, which means it has the unitary operators, you remain quantum states, right? You have to design algorithm. So, I mean, it works for quantum computing. Okay. Very often, the very simple algorithm, classical algorithm that you take for granted doesn't work. Very simple ones doesn't work. So it's very restricted. So despite all these challenges, there has been some progress to solve scientific computing problem. So there are a lot of progress in quantum information theory here. I'm talking about quantum computer for scientific computing. So for example, there has been some quantum linear algebra solvers, which has been developed. One of the first earliest one is called the HHL algorithm. So the complexity is like this. So you suppose you want to invert a matrix M, solve X equals Y. So the complexity of this algorithm depends on the maximum norm. Here the maximum norm is just the maximum entries of matrix in absolute value. Divided by eta is the accuracy requirement. And then it depends on kappa, which is the condition number of the matrix. So kappa square. S the sparsity. So it's the number of non-zero rows or column entries. And then you have this logarithmic term, which is not very important compared to the one. And then more recent algorithm called CKS algorithm actually remove the square from a condition number, and you no longer have this 1 over the precision eta. It appears in this log term. So that's pretty much the best you can do. So it really depends on condition number and sparsity. All right. So of course, once you know how to solve a linear algebra problem, you can solve linear ODE or PDE, because once you discretize the spatial derivative, it becomes some time or space derivative becomes a linear algebra problem. All right. So you can use this algorithm to solve PDEs. But unfortunately, we know, I mean, these are differential operators usually, if you discretize, it's year conditioned. So for example, if you solve an elliptic problem, I mean, the condition number is like n squared, where n is the number of mesh points. So if you put n squared here, I mean, it's a big number. So therefore, actually, for low dimensional problem, you do not have quantum advantage. But you do get quantum advantage for very high dimensional problem. Okay, so I mean, quantum computer is really good for very high dimensional. That's why people want to solve it body shortage equation, because that's very high dimensional. So you do get quantum advantage for high dimensional problem. However, I mean, I just want to emphasize this complexity is really for subroutines. You start from quantum state to quantum state. So what you output is really the quantum state of X. X cut, not X itself. From here to there, you have to do a classical measurement, right? You have to measure it. So now we want to first concentrate on solving PDEs, ODEs, all right? So as I said, the quantum computer is based on quantum mechanics solver. Okay, so the best equation for the quantum computer to solve is Schrodinger equation. So the algorithm solving Schrodinger equation usually is called quantum simulation. And they're actually used so-called Chaucer splitting, which is really what we call strong splitting, okay, in the mathematical community. So this is Schrodinger equation where H is the Hamiltonian, which has two parts, kinetic power, kinetic energy, and potential energy. All right. So clearly, if you start with the initial data and you just, this is the solution evolution operator, okay, where H is Hermitian. So therefore, e to the minus I th is the unitary. Okay, so it's a unit operator. So if you start with quantum state, you evolve by this unitary operator, you end up at the quantum state. So it likes this kind of operator where H is Hermitian. So you want a unitary operator. So if you do that, it's called quantum simulation. And actually, you can compare with other discretization methods. So if I can, for example, here I use the Liouville equation. You can either do quantum simulation or can use find a difference or a spectral method. And you can compare, you do see that whether you want just subrouting or you want to compute the observables. So this is a complexity. For example, if you use quantum simulation to solve the Liouville equation. So D is the space dimension. L is parameter that has to do with regularity. HL, data is HL, right? Epsilon is the air. So as you can see, it's like D to the power 2 plus 2 over L. And it's over epsilon squared, epsilon to the power 2 plus 4 plus L. So that's the cost of quantum simulation. If you use spectral method and then solve a linear algebra problem, then you get T to the 3 here and epsilon to the power 4. So clearly, quantum simulation gives you the best result. In terms of complexity, it is more efficient than other methods. So therefore, it's very natural to ask the following question. If I'm given a general PD or ODE, can I do quantum simulation on these PDEs, right? Can you use the most efficient quantum simulation to solve a general PD and ODE? Okay. So if that problem is taken care of, then these are linear, Schrodinger equations are linear, remember. Then how about the nonlinear PD? Right. So these are the questions we are very interested. So about the first question, so joint work with Nana and you is our postdoc. So we find a way that systematically can what we call a Schrodinger every PD OD into a Schrodinger equation. All right. So for example, here we have a very simple heat equation in D dimension. All right, initial value problem. So here X is RD. So the idea actually is very simple. So we introduce a new function which depends on T and X and another variable P. But P is a scalar. All right. It's actually very simple. E to the minus P times U, but P is positive. Right. Now it's very easy to prove that if you satisfy this heat equation, then W actually satisfies this third order PDE. All right, with the actual P derivative. Well, from W to U actually is very easy. Actually, just integrate over P, you get U. So just like take a moment, zeros moment. All right. Or even because U does not depend on P. Actually, E to the P times W is independent of P. So actually, can take any point in P star, positive, and you evaluate this quantity get U. It's very simple. So now, first, is this a good PDE? Okay. It's very easy. So now if you take a Fourier transform X, okay, if you take Fourier transform on X, then you get this following, how is Fourier transform W, then you get, this psi is the Fourier mode, all right? So you get this, actually it's a linear transport equation where the wave moves from the right to the left, right? You get negative sign here. So this shows that you do not need a boundary condition at P equals 0 because the wave is moved from the left or right to the left. So the P equals 0, no boundary condition. You need a boundary on the right, but you can truncate for P sufficiently large because solution decays exponentially in P. You just stop at some P large enough for your accuracy requirement, right? So first, it looks like it's a good PDE, okay. And then, what's its connection with Schrodinger equation? Okay, so this is our new PDE, and actually we can extend as an even function to the entire space. All right, then you have the minus the length of P. Absolute value of P. P is a scalar. So now if you take Fourier transform on P, then you get this equation where eta is the Fourier mode for P. Now clearly this is a Schrodinger equation. For each Fourier mode eta, it's a Schrodinger equation. All right. So you can solve, you let your quantum computer solve this equation. So first, of course, you have to take a discrete Fourier transform on this equation. So the eta there is a discrete Fourier modes. All right, it's a finite number of them. Then you can put this into a quantum computer, and then you do inverse Fourier transform. Well, actually, there's a quantum Fourier FFT. Okay, so that's available. You can use it, this quantum FFT. So you have to use quantum FFT to between Fourier modes and the original variable. Then you take moments to get the unit. And these moments can be easily done at a quantum computer, something called a swap test that can be done for inner product. If you use a quadrature rule to describe this moment, I mean, there are existing quantum algorithms you can use. All right. So therefore, essentially, now we have rewritten the heat equation in one dimension higher, or one space dimension higher, which now in the Fourier space is the Schrodinger equation. All right. So we sort of Schrodingerize the heat equation, which is a little bit strange because heat equation is dissipative, and this equation actually conserve energy, but it's in one dimension higher. So how about general dynamic system? All right. So here now we talk about general high dynamic system, which includes both ODEs and also PDEs. Once you discretize in space, then it's a system of ODEs, right? So of course, this problem is generic enough for ODEs and the discrete PDEs. But in general, of course, A is not Hermitian. Okay, A is not Hermitian, and so but we can write A. We can decompose A into H1 plus I H2, where H is A plus A complex conjugate. Transform Dagger means transposed conjugate. Okay, so H1 is A plus A Dagger, and H2 is A minus A Dagger divided by 2I. Clearly, both H1 and H2 are Hermitian matrices. All right. So A can be written as one Hermitian matrix plus I times another Hermitian matrix. But of course, now this IH2 is good because if you put it over there, the evolution operator is unitary. E to the IH2T is the unitary. Okay. However, H1 is does not give you a unitary operator because E to the H1T is not. So now we use this transformation, we will call warped phase transformation. You let the V, which now depends on T and P, to be E to the minus PU. Then this U is going to put another derivative on this H1. You get H minus H1 times the P derivative V, where H2 remains as is. All right. And now this one, if you take a Fourier transform P, you get another eta, like what we did for the heat equation. So you get another I here. Now the right-hand side becomes a unit. You have I times the Hermitian matrix. Then the evolution operator of the solution is a unity. Okay, so apparently this works for general dynamic system. So actually we have played with all these different examples, linear Black-Scholes equations, linear transport equations, for example, neutron transport, radiative transfer for Planck equations, even volatile Fourier. So this.
What about variable coefficients?
You mean?
I mean, that change of variables Fourierized works for constant coefficient.
No, are you Stan?
I am Stan, always have been.
Oh, Stan, how are you?
I woke up for you. It's 5 o'clock in the morning here.
Thank you. Good question. We haven't worked on it, but that's a very, very good question. I think you mean the non-autonomous A depends on T.
A is a function of T, nice and linear, but a function of T.
That's a good question. Yeah, there's actually quantum simulation for time-dependent emission. It's not the best of I like, but it exists. In my opinion, it should be done better. But so far, the people use it. Because you can, if you do child splitting time step, and you sort of each time step you pick up one H of T. That's what people do these days. But that's something that we should improve.
But you can't take the Fourier transform so cavalierly.
I understand. Yeah, that's something we haven't worked on. It's certainly it's our outstanding question.
Okay.
Okay, thank you. Okay, now how about nonlinear OD and PD? All right, so far we take care of linear PD, at least for autonomous system. Okay, non-autonomous that remains to be done, remain to be improved. So here we are actually nonlinear ODs and also nonlinear PDs, but we are also interested in not solving this equation for one initial data. We are actually solving the equation with m initial data. Very often the case, for example, if you do uncertainty quantification, you have to run many samples, and in the end you take ensemble average. Okay, so we are talking about solving the PDs with initial data, OD and PD, nonlinear. Well, of course, I mean, for this community, I do not have to convince you how important it is to solve nonlinear equations like fluid dynamics, molecular dynamics, financial problems, and machine learning, all nonlinear dynamics, right? So there are a lot of difficulties with discontinuities and shocks and so on. And another difficulty is curse of dimensionality. So very often, the reason we want to consider multiple initial data is very often if you have a statistical method, Monte Carlo, for example, if you have a certain configuration, if you solve a stochastic problem, you have to solve this PD many, many times. Okay, with different samples, you take average. So here, these are the parameters you try to get quantum advantage of. Here, D is the space dimension of PD, capital D is the number of ODs, epsilon is the error, and T is the computational time, M is the number of the initial data you want to run. So these are the parameters which we want to see whether we can gain quantum advantage of. So we do not have an algorithm for general non-nonlinear PD. Well, we can do it, but we cannot prove quantum advantage. So I'm going to show you two examples where we can do it and with proven quantum advantage. All right. So one example is Jacobi. Another one is hyperbolic, nonlinear scalar hyperbolic equation. Okay, we cannot do systems, but just scalar. So first, it's very difficult to do nonlinear problems. So this is the paper published in Physical Review Letter by this guy L, which says Lloyd, which this L is this. You remember this HHL algorithm? Well, that's this L, the professor at MIT. So he tried to develop this nonlinear quantum mechanics computer to solve nonlinear PDs. So this is his conclusion: is that we would like to note that we believe that quantum mechanics is in all likelihood exactly linear, and this above conclusion might be viewed most profitably as further evidence that this is indeed the case. So this is sort of a negative conclusion. He tried very hard to develop a nonlinear quantum computer, but it doesn't work basically. Of course, he said, of course, if your research can prove otherwise, it will be great. So so there are only two routes. One is just completely forget what the Feynman imagined about a quantum computer. You forget about this fundamental quantum mechanics. You completely have different ideas. Well, that's what they try to do. Of course, they did not succeed. Then the second approach is make the problem linear. All right. If you cannot have a new nonlinear quantum computer, it just makes things linear. So before us, there has been an attempt in this direction, which we call a linear approximation. So basically, you're based on linearization. You linearize problem on constant, around the stationary solution, and so on. And the most appealing approach is called a Kalman approximation truncation. Basically, for example, you solve a Riccati equation, all right? Du dt was minus u squared. Let u squared to be w. You write it for w, then you have w squared. You write w squared as another variable. Then you have this infinite hierarchy. We all know, it's like moment of closure. From Boltzmann to fluids, you have this infinite hierarchy. You have to stop sometime. So in the end, they said, okay, the last equation of stop is always a nonlinear term, right? So the Kalman represents. Of course, we all know, this kind of technology, there's only so much you can do. It's probably okay for weak nonlinearities, very short time, right? What we want to do is actually, we call the linear representation, which means we want to find a linear map, a map which maps nonlinear problem to linear exactly without any truncation, no approximation. The model is equivalent. But before us, there's some ODE work. Okay, for ODEs work by some plasma physics, where they use so-called a Cookman von Neumann approach, right? So they could do it for nonlinear ODE. Move to phase space to get the linear transport equation. But for PD, before us, there's no work. So now let's come to Jacobi. So thanks to Stan, actually a few years ago, not too long ago, we wrote a paper published in the Best Applied Math Journal. So actually we use this level set method to solve the Jacobi equation. So here's Jacobi equation in d dimension, all right? So we know that if you take gradient of Jacobi equation, if s is phase, u is velocity, then you can write equation for u, which actually is a hyperbolic equation, all right? So you get gradient h of u. So the idea of a level set is that now I introduce a level set function, which depends on t, x, and p, but p is the same dimension as x, right? So when p equals u, phi is 0. So that's the definition of level set. And so, of course, now we double the dimension, all right? From d-dimensional problem to 2D dimension. Now it's a basic calculus exercise. It turns out this phi satisfied as a linear Liouville equation, where h is the Hamiltonian. Now, because I project P equals U. So here now H depends on X and P. So it's really a Liouville equation. And the initial data of phi is very easy. Let it to be P equals the initial data of U. So clearly, if P equals U, you give 0, right? So that's really the zero level set give you the solution U. All right. So of course, quantum computer can solve the Liouville equation because of linear PDE. However, once you solve it, in the end, you have to find a solution. You have to find a 0 level set, which is very easy for classical computer. For example, if you use MATLAB in 2D is the contour, in 3D is the isosphere. But as I said, this quantum computer, it's very difficult to find a 0 for. I mean, it's very expensive to find a 0 function. Okay, quantum computer doesn't know how to do it. So instead, what we do is that we introduce another function called psi, which is a delta function of this phi level set. And actually, remember, we have to solve it for m different initial data. All right, so we want to solve m different initial data. Now we can even superimpose, linear superimpose. We linear superimpose for each initial data is the index denoted by k. For each initial data, we get phi k. Now we superimpose all the k and normalize it, which means we superimpose the delta function of initial data. This is like ensemble average. Okay. It turns out if phi satisfies the Liouville equation, psi also satisfies exact same Liouville equation. All right. So the first advantage now, before you have to solve the Jacques-Louis equation times to get ensemble average. Now we only have to solve it once because now we already linear superimpose the initial data and the equation is linear. Okay. So it means if you do Monte Carlo simulation to get ensemble average, you just have to solve this PDE once. So we have quantum advantage over M. So next, what's the relation between psi and the original solution? It turns out if you take so-called moments of, you get so-called what is called a physical observable. So you multiply psi by a function of P, all right? It depends on what you choose P. You can choose P equals 1, P and P squared. And the zeroth moment actually give you, if you interpret this Liouville equation as a semi-class limit of Schrodinger, then these moments give you nothing but position density, momentum, and temporal kinetic energy. With the momentum here, you have U, which is green S. Okay, so now you take moments, you get the solution of the original equation. It turns out these moments, because in integration, you can use quadrature rule. Once you use quadrature rule, then it's basically inner product of two functions. And this quantum algorithm called the swap test, which can do this. So instead of finding zeros, it become probably finding the moments. And the moments give you the observables, which is relatively easy to do by quantum computer. All right. So that's some details. Here's the quadrature rule, and you can write a G at the grid point times psi at the grid point. So that's really the inner product. So this quantum algorithm, the swap test can do the inner product. We have to emphasize this solution give you so-called multi-value solution. All right. This is really method characteristic, give you the multi-value solution. So multi-value, so for example, this Jacobi has been used for as a level set method to solve interface problem and the work of Gaussian session. So what is the multi-value solution? So you have these two circles, and this wavefront, which is say expand in the unit normal direction by speed 1, then very soon this curve will touch. And the viscous solution give you this solution where this multi-value solution satisfies linear superposition principle, so actually get this overlap with density superimposed. Why you care about this solution? I mean, a lot of applications you get this kind of solution. For example, geometric optics, where you care not one arrival, but the so-called multiple arrivals. And also in semi-class limit of Schrodinger equation, all the high frequency limit of high frequency wave, you always get iconic equation, and then you have to use this multi-value solution. So in the language of shock wave, if you solve Berkeley's equation, of course, usually you get this multi-valued, and of course, if you take a cut by equal area rule, that's the viscous solution. So here we only generate the multi-value solution, not viscous. So these some details. Now you solve the Liouville equation by finding the difference for the in time. You can do up to upwind. Then you can put it in a linear system. So what quantum computer does is that you put all the time steps into one big vector. All right. So here's the first index is a real time step all the way to MT, the number of time step. You put it into a big matrix. This coefficient matrix is sparse, of course. Then sort of course, kappa in general is not Hermitian, but you can make it Hermitian matrix by use this dilation. And then you solve this linear algebra problem, mx equals y, and assume it's 2 to the power m times the 2 to the power matrix. The classic algorithm, if you do say Gaussian elimination, usually it's matrix size cube, right? Near that. But it was quantum algorithm because then you take a log of 2 to the power m. So that's where you get the exponential advantage. Here are some details. As I said, well, actually in the quantum computer, you do not really solve mx y. you solve M times quantum state of X equals quantum state of Y. So this is actually your output. And if you want, so complexity actually depends on how many, so this is the matrix. You have to put the matrix into a quantum computer, which is non-trivial actually, can be very expensive, all right? So usually this was done through something called oracles, which is really like black box. I don't like this terminology, but that's what is being done, okay, through some oracles. So then you ask how many times these oracles are being queued. So this is called query complexity. And in our case, actually, because we take the moments, so the moments can be interpreted by this function G. So it's really, this is the quantity, the moments we output is really like expected value, all right? And here, of course, you also have the oracle to encode this G function. So you have two oracles, one for M matrix, one for G. So this is one realistic implementation of these oracles. So this is always the oracle that encode the matrix M. If it's sparse matrix, you have to remember these non-zero entries, the position of non-zero entries. So you need another oracle OF. Right. So then you count how many times you have to use these oracles. Some details. Basically, we just do Chapidolo rules for the moments. So these are some details which I've just skipped. And so this is the computational cost. Q is the cost of this quantum algorithm. It depends on the space dimension D. T is the time of the computation. Epsilon is the error. All right. Does not make sense to you, but now I want to compare with classical cost. So C is the classical cost. I divide class cost by quantum cost. And then here, M is the number of initial data. Clearly, classical is M times longer because you have to do it M times. Now algorithm once. And I have D to some power and 1 over epsilon to the power. And you want this to be large. Okay, so therefore R1 and R2 need to be large. So you want them to be positive, need to be positive. So here's some examples we checked. So if it's Hamming-Jacobi equation for D dimension, D plus 1 stands for time. So as you can see, if dimension is large enough, you get positive R1, R2. So really for high dimensional problem, all right? D has to do with the initial data for the moment, just forget it. If D is bigger than 4, you get quantum advantage for dimension. If D is bigger than 9, you get quantum advantage for the accuracy, all right? And you always get quantum advantage for M because we only have to solve different initial data once. So this is for scalar hyperbolic equations where the level set method also works. Again, the conclusion is similar. For certain ODEs, unfortunately, you never get quantum advantage. Okay, so you always get negative, but of course we get advantage for M. So for general PD, what can you do? Well, for example, if a Navier-Stokes equation, you can take a spatial discretization, then it becomes certain ODE. You can use this level set method. But unfortunately, as I said, OD already cannot have a quantum advantage. Of course, you find a difference. Or vortex method. You can use for incompressible Navier-Stokes, you can use vortex method, which is like particle method. And none of this give you quantum advantage. Okay. The reason is that the dimension is simply too high. From Hamming-Jacobi from D to 2D, that's fine. But for Navier-Stokes, if you discrete in space, they have this big certain ODEs. That's dimension is simply too high. So you do not have advantage. However, we always get advantage if you have to run it many times for M. So the conclusion before the next section is basically this. We give us basically the first quantum linear PD solver based on what's called the linear representation in contrast to linear approximation. Here we have no approximation. Okay. This is equivalent. So we can demonstrate the advantage in this number of initial data, space dimension, and accuracy. But actually, when we talk about complexity, we include the computation moments. So include the measurement step, which was not the case in the previous work. When people talk about it, even for linear PD, they only talk about the complexity of quantum subroutines without doing this measurement. So our advantage actually includes the measurement to output the physical observers. Of course, well, this is only first step. There are lots of open questions. So for general PDEs, I use Navier-Stokes equation as example. Viscous solution, we do not know how to do. Because for viscous solutions, the closest to this formulation is Young's transport and collapse, and also this Lyon's patent kinetic formulation. But there you have this linear operator, which is fine, but you have to do this collapse or projection to local Maxwellian. And that we do not know how to implement for quantum computer. So that's open. So a lot of open problems. Also very high dimensional dynamic systems like molecular dynamics. Okay, dimension, if you go to phase space, dimension simply too high. So you lose quantum advantage. So they're major, big open questions. Finally, I go to this topic of uncertainty quantification, where I joint work with Francois goes. Let's start with a very simple ODE example. So very often, you have coefficient in the PD ODE, which are uncertain. There are many examples because all these PDs are done through truncations, coarse graining. All right, so this coefficient can depend on this uncertain variable Z, which is a random variable in D dimensions. So of course, usually you solve this problem by Monte Carlo, or people use stochastic collocation. It's sampling-based method. You have to take a lot of samples to solve this equation many times, then take a sample average. All right. So you really very often you have to do a lot of simulation. So actually, Francois introduced this Fourier transformation, which is is basically what we did for short generalization. So he introduced a new variable u, which by adding another variable w is a of z times e to the minus wx. And here w is positive. And then you can easily show that you actually, little you solve the ODE, but now you solve this linear transport equation. But now this certain coefficient appears only in initial data. Okay. The equation itself has no coefficient dependent on z, which means if I want to do Monte Carlo and take on sample average, I just have to take on sample average of the initial data. Then I only have to solve this PD once. You get sample average, right? Of course, you don't do this for classical computer because you add higher dimension, people will kill me. And I know this idea more than 10 years ago. I never know how to use it. Finally, quantum computer, you are allowed to go to a little bit higher dimension. That's why this can be useful. All right. And that's ODE, you can do PDE, for example, heat equation with this heat conductivity can be uncertain, use same transformation. That actually get this third order PDE, which we have seen before. With the initial data, which can be, with this certain variable, you can take a linear superposition. And how about the wave equation? Actually, for wave equation, the same idea doesn't work because you use the same transformation, then actually get this mixed derivative, okay, which is bad equation actually. So du dt plus du dxy is a bad equation. All right, so it's your condition. What you can do is actually you use another transformation, which you take square root, then actually get two derivatives in W here. And this third order PDE turns out to be good PDE. Because you take Fourier transform, you see on W, you get the linear transport equation. It's a nice equation. So that's what we do. You can do it for Schrodinger equation if the potential has certainty. If you do the same transformation, actually, this kinetic energy becomes actually get free Schrodinger. This equation also get another second derivative. So it becomes free Schrodinger equation. All right. Of course, with variable mass. Now you may say, okay, this A of Z is too special. Well, you do get quantum advantage, all right? Always on M because you only have to do Monte Carlo, just do one simulation. And you also get some advantage for epsilon, for accuracy when the dimension is high enough. All these different type of PDEs. Now you may say, okay, look, this A of Z is too simple, right? It's too simple. So how about more general A that depends on both X and Z? We cannot do the most general case, but we can do the case if A can be written as a linear superposition of the function Z times function. This is not the most general case, but it's the case that people do in this business. For example, if a general stochastic process, can be this Calhoun-Lowe theorem. You can write it as a linear combination like this form. If this is a basis, if you use a basis in X, then the coefficient only depends on Z. Also, in the uncertainty quantification, when people use so-called stochastic looking method, where suppose you know the probability distribution of Z, then you can find also normal basis like molecular chaos, polynomial chaos. So you just construct orthogonal basis like a Hermitian basis. Then you have a coefficient which only depend on X. So this fairly general. For what people do these days. All right. Now, in this case, actually, now you need a W that has to be the same dimension as L. Instead of adding one dimension, you add an L dimensional vector. Then you get a similar equation, except here you have each component, you get this third order derivative. All right. So that's what you can do. Non-linear PD, ODE, again, you can discretize in space, and then use level set approach to make it linear, right? And of course, you can always gain advantage on the number of the initial data. not necessarily for other parameters, as I mentioned earlier. To summarize, so this is actually our philosophy to solve this problem. I mean, classical computation, we know that we hate high dimension, all right? Because the dimension is a major bottleneck. So very often you start with high dimensional problem, you make all the effort to do dimension reduction, coarse graining, mean field approximation, moment closure, all these weapons to make it a low dimensional, but the price is paid. You may start with linear equation, you end up at nonlinear, with uncertainties and other troubles. So our idea for quantum computation is that you go backwards, you lift to phase space, okay? So you sort of avoid those troubles once you go to higher dimension. So, I mean, nonlinear problem may become linear, and certain problem becomes some kind of a certain, I mean, you have less trouble. So that's our way of doing this. So you really have to rethink, different from classical computation. I mean, you have to go opposite direction. But of course, you cannot afford too high dimension. So you have to find something between. You do not really want to go to M-body Schrodinger equation. That's a little bit too much. So the question, can you go before, not to the quantum level, can you find some linear representation? So this take-home message, when you have trouble in low dimension, all you need to do is, this is wrong. So you have. Thank you very much.
You can test this method even in a classical computer.
Yes, definitely. You can check whether they are right, but you cannot prove quantum advantage because quantum advantage shows in high dimension. Classical computing can show this algorithm works. It gives the right result for low dimensional problem. Yeah, that we can do. Yeah.
So for example, for the wave equation, for the heat equation, you can do Schrodinger and the Fourier.
Yeah, of course, we saw video plot. Yeah, looks it is right. It gives exactly the same.
And you don't lose the properties like positivity or these conservation laws that you want to present.
That depends on how you discretize. If you use spectral method, of course, you lose positivity. Yeah, I mean, so far we haven't been bothered. The only thing we like to do better is we have the e to the minus absolute value of p. So if you take a Fourier, discrete Fourier transform, you do not get spectral accuracy, right? Get first order. But for quantum computer, first order force doesn't matter. Because if you take log, I mean, it doesn't matter, right? You just need a few more points. But mathematics would be better if you have more smoother function to take before you take discrete Fourier transform. So there are some polishing, fine tuning you can do. But it's just the general framework that we are pushing. It's our way of thinking. You may do this differently, but we think that the idea is to go to a little bit higher dimension to avoid some of the trouble. So that's our way of doing this business. Of course, as you can see, for nonlinear problem, there are major open questions that remain to be done. So, but it's always interesting because quantum computing is big business in China, US. So they're always interested in having an algorithm to test. So really want to see the boundary of a quantum computer, right? At the beginning, people think quantum computer can solve both, Schrodinger equation. We really want to see how much it can do. So we try to find the boundaries. So far, these are the examples we found it can make it work. But with Scala solutions, other PDs, so far we don't know. Yeah.
What questions?
This one.
Just a small comment. So can you comment on how many qubits you would need or what the circuit depth required would be if you wanted to beat a classical simulation on one of these?
If you want to produce reliable computation that people can use to predict weather or something like that. Well, my colleague, she's actually a physicist. She probably can give it better. I always ask her this question. She said maybe million. You need a million qubits. Well, IBM now has 400. They predict by the year this year, they can have 1,000. So 1 million. I don't know how many years.
People are always asking the size, but actually that's not really the main issue. People can produce millions of qubits already, but you need to be able to control them. So all the operations that you do, all the unitary operations, the gates, you need to be able to do them, and then you need to be well controlled. You need to be able to control the errors and the errors to correct them. And for these, you need even more qubits. So per single qubit, you probably need to replace like 1,000 physical. So I guess on the order of millions for things like RPDs. However, what we're hoping for with this randomization method is that instead of using this universal computer, digitizing it, if we can find a natural quantum system that can realize these Hamiltonians and to do this randomization method becomes simulation rather than just computation. And I've been speaking to experimentalists about this, so they're thinking about it, and some people say yes, some people say no, maybe they can do it in your labs. But if you find those systems, we don't want very, very high resolution on our solution, then maybe that's much more near term. So that's also why we're looking like to the radicalization.
So, on the simple example, are you able to quantify the noise due to the qubits themselves?
Well, of course, our work does not involve that, but that's very important. This error correction, of course, is very important.
So it's ensured for the HHL, the original HHL algorithm for matrix inversion that is very, very sensitive to noise. So that for these algorithms, you really need to have these error correction schemes. However, I'm not sure about our sharingization algorithm, so we haven't done the error analysis kind of for that. But if we can find this natural quantum system that can do it, like yeah. So maybe it's a little bit better. I don't know.
Yeah, Bruno.
Yes, and can you tell us when it is expected that such a quantum computer will exist?
I don't know. This reminds me of what people always ask about the nuclear fusion. When,
It exists right now. Like
Yeah.
Google will tell you we have one. We've had one for years, and IBM will tell you they've had one for years. But it depends on what you have to use it for.
Yeah.
It's like we were talking about earlier about analog computing. So when classical computers first started, actually the most popular models was not the Turing kind of digitized kind of model, but analog ones. So if you want to solve only a subset of particular problems, then you find the classical system and the natural dynamics to solve that particular. So yeah, so I'll say it depends. Like for these specialized ones, I would say it's probably much more near term. And again, that's what we're hoping for with these randomization methods. For intelligibility systems, just to solve classes of particular PDs. Like some PDs which look slightly more like Schrodinger, maybe that's more near term. The ones that are much more distributed. Yeah, but if you're talking about the ones where you can fully universal, fully error corrected, then unless we have a big breakthrough in error correction, then I have no idea. So yeah.
Yeah, so these are the questions in the chat. Maybe what this gentleman thinks is not in the next decade.
Yeah.
Maybe analog.
Yeah, but the second question, if you can make your method NISQ friendly. So people in the audience who don't know what NISQ is, so it stands for noisy intermediate range computing. So yeah, I'll scale, yes. Noisy intermediate. So and this is stuff that for research like here, like as well, if you like NISQ algorithms. Yeah, like again, we can make these like into sort of variational type algorithms, but for these it's very hard to quantify exactly how much they're better than classical, right? So because what a lot of this NISQ algorithm does, it relies a lot on the power of classical computing. Because here with these algorithms fully quantum, like there's nothing classical. But the NISQ kind of mindset is like, can we take away what classical computers are already good at and combine it with some quantum processing? But again, as soon as you put in any classical processing, you're interrupting the quantum, computation somehow, and you're taking that away. So it's a short answer is yes. I mean, we can make them, but that's not the direction I think we want to go for. But we kind of believe that one day there will be these error-corrected computers, and once we have them, what do we do with them? Because I think there's not a good answer in the community, despite all the attention, on what we can do with it, even if we had it.
All right, thank you. I think it's time to stop. Thank you again.
Thank you very much.